Could you hear that?
Did you press play? I can hear you, but press play on the thing and
Uh,
I'll tell you if I can hear it. I can see it.
just one sec.
It's the little ticker box there on the screen. The dialogue
Yep, and then
share sound.
More commonly known as the
That's it.
Leibniz
Buzzer.
integral rule, differentiating under the integral sign. More commonly known as the Leibniz integral rule, differentiating under the integral sign is a method of calculus used to solve integrals of a specific type. These integrals are usually more difficult and cannot be solved through standard elementary methods. Originally, these integrals appeared impossible to solve or required high complex computations or technology, such as Wolfram alpha, to solve. The specific integrals that are evaluated using this technique can be thought as belonging to a certain family of integrals, depending on a parameter. Usually, we use t. This rule states that an integral from a as a function of x to b as a function of x, of a function in terms of x and d dt, where the function in terms of x and t is continuous and differentiable, and the limits are also continuous and differentiable. The derivative of this integral can be expressed as this. Furthermore, if in a special case that the limits are constants instead of functions of x, this formula can be reduced to a simpler form. And thus, differentiation under the integral sign states that under certain conditions, one may interchange the order of integration and differentiation in an integral.
To help better our understanding of Leibniz integral rule, we will consider the following example. We are going to integrate x cubed minus 1 over ln x between 0 and 1 with respect to x. At first glance, the integral seems resistant to standard integration techniques like substitution and integration by parts. Therefore, we have to use differentiation under the integral sign to evaluate it. Let's start off by defining a general function. We'll call this function I of t. This general function is the integral from 0 to 1 of x to the power of t minus 1 all over ln x dx. What we want to do with this function is simplify the integral and then find the value of I when t is equal to 3. This in turn will be the equivalent of the original integral we are trying to evaluate. So the first thing we do to try and simplify the integral is finding the first derivative of I. Now that we have the function in this form, we are able to use Leibniz's integral rule to further simplify the integral. So now the integral is rewritten as the integral from 0 to 1 of the partial derivatives with respect to t of x to the power of t minus 1 over ln x dx. Now, if we were to split up the fraction into two parts, x to the power of t over ln x minus 1 over ln x, and if we were to take the partial derivative of minus 1 over ln x with respect to t, that term will just disappear. Now we remain with the partial derivative with respect to t of x to the power of t over ln x. Since we're taking the partial derivatives with respect to t, the x stays as a constant. That means we take the first derivative of x to the power of t, which is equal to x to the power of t multiplied by ln x. Now the ln x's cancel each other out, and we're just left with the integral from 0 to 1 of x to the power of t dx. And now the integral is simple enough to just integrate using the power rule, which leaves us with x to the power of t plus 1 over t plus 1, from x equals 0 to x equals 1. And with a bit of working out, this is just equal to 1 over t plus 1. Now we need to get back to the original function in its simplified form. This part is simple. All we have to do is integrate I prime. Now that we've done that, we are left with ln t plus 1 plus c. To evaluate the value of c, we'll sub in a value of t into the original integral to compute a value we know the answer to. So we're going to use t equals 0, because as you can see from the original integral, when you sub t equals 0, you just get 0. And therefore I of 0 is equal to 0. Now we just use the value we just computed by subbing it into our simplified form of our general function. We will then find out that c is equal to 0, so therefore I of t is equal to ln of t plus 1. And now that we know the exact expression for I of t, we now just sub in the right value for t so that the integral is equivalent to the original integral we were evaluating, which means we sub in t equals 3 which then gets us ln 4.
For the second example that we're doing, we'll be integrating sine x over x dx from 0 to infinity. First, we'll make a new parameter for it. So we'll have sine x over x times e to the power of negative tx. From here, we'll sub 0 into it, and we'll find that it actually gives us our initial integral that we're trying to figure out. So now we try to differentiate this in terms of t, and what we find is that it gives us the partial derivative in respect to t. So we do that, and we find that it gives us negative x sine x times e to the power of negative tx over x. So now we can cancel out the x's, and we'll be left with a negative sine x times e to the power of negative tx. From there, we want to use integration by parts to get negative e to the power of negative tx outside of cos x plus t sine x over t squared plus 1. When we let t approach infinity, the e term, due to it having a negative power, will actually be in the denominator, and as t approaches infinity, that will cause that term to approach 0. So then we get 0 minus, and because we sub 0 in, we just end up getting negative 1 over t squared plus 1. Additionally, t has to be above or equal to 0 for this to work, so that e can stay in the denominator instead of going on the numerator, because then it just won't work. We integrate I dash t now to get negative inverse tan t plus c, and integrating I dash t just gives us it again, so we can make those equal, and so then we let t approach infinity, which ultimately results in giving us negative pi on 2 plus c equals 0, which then means c equals pi on 2, so therefore it equals negative inverse tan t plus pi on 2. Now we just sub t equals 0 in, which gives us negative inverse tan 0 plus pi on 2, which equals pi on 2, which is our answer for integral of sine x over x dx from 0 to infinity.
Alright, that's it for that one.
Okay, thanks very much, Justin. That's a good job.
Any questions or?
No.